So next, we are now going to be talking about linear correlation. So before we talk about that, let's talk about a scatter diagram, also known as a scatter plot. So a scatter diagram is a graph that shows relationships between two quantitative variables. So remember, quantitative is all about numbers. So there should be two numbers measured on the same individual. Two numerical values on the same individual. So each individual in this data set is represented by a point in the scatter plot. We say the explanatory variable is plotted on the horizontal axis. Right? Remember, explanatory variable, that's going to be the x values. So this should be explaining the response variable, and then the response variable, of course, will be on the vertical axis. All right. Next, correlation. So a correlation will exist between two variables when the values of one are somehow associated or related with one another in some way. So if there is some sort of relationship between these two variables, we say that there is a correlation. A linear correlation exists when between two variables when there is a correlation. And when you plot all the points on a scatter diagram, you get an approximate straight line. Now, just because you do have a correlation doesn't mean one affects or one is causing the other. That's a very common thing you will see in the media all the time. A lot of times you'll see something like there's found to be a correlation between SAT scores and fruit consumption. Right? So then people say, oh, well, then I need to make sure that my kid has lots of fruits. That way they get high SAT scores. But that's not what that means, right? There's just a relationship between the two. So here's another silly example. So there is a correlation between shark attacks, the number of shark attacks, and the number of ice cream sales. Thus, sharks must like people who have eaten ice cream. Right? No, that's completely ridiculous. Of course not. Just because there's a relationship between shark attacks and ice cream sales, there could be a number of different reasons why that could be the case, right? If shark attacks are increasing and ice cream sales are increasing at the exact same time, right? It could just be that it's summer, right? At summer, it's hotter out, so people are more likely to buy ice cream and more likely to get shark attack because there's more people in the ocean, right? So just because there's an association, a relationship between two different things does not mean that one causes the other, right? Doesn't mean fruit causes SAT scores to go higher. There's just a relationship between the two. You'd have to do way further research to have that cause and effect. All right, so let's look at this. So let's determine what kind of scatter plots these are, if there is a correlation and what they may be. So if we look at the first one, right? The first one, it's kind of seeming like everything is going up, right? So this is going to be a positive linear correlation, probably. We'll talk about specifically how we know one way or the other later, but if we had to guess, we would say there's probably a positive linear correlation, which means, right, that as x increases, then y is also increasing. Part B, we can see that this, right, part B is typically going in a downward direction, so this is probably going to be a negative linear correlation. So again, as x increases, what's happening to the y values? we see that the y values are actually decreasing this time, right? So that's what happens with a negative correlation, linear correlation. Part C, you're just kind of all over the place, right? So there's really no correlation occurring. They don't really seem like they're connected in any way. They're just kind of all over the place. And then lastly, we can't, like we said, we can't have correlations that just clearly are nonlinear. Right? So clearly there's a correlation here. It's just not going to be a linear one, right? Some people might remember this, the word parabola comes to mind. So this is like quadratic, but we won't talk about those. We're only going to be talking about linear correlations in this class. All right, so let's look at some examples. So problem number 2 in your handout. Because cola tends to replace healthier beverages and cola contains caffeine and phosphoric acid, researchers wanted to know if cola consumption is associated with lower bone mineral density in women. So listed below are the typical number of cans consumed in a week by women and their bone density. So looking at this, what would we say is the explanatory variable? Which one would be the response variable? So would it make sense that cola could be an explanation of the bone mineral density, or that the bone mineral density could be an explanation of the cola? Now again, we don't know for sure, but if we had to guess, right, we would say that the explanatory variable would probably be the number of colas. The response variable would probably be the bone density, right? If there was an association, right, if there was a cause and effect, cola would be the one to affect bone density, not the other way around, right? Now again, we don't know for sure. We would have to prove it using different methods, but if this was the case, we would say that the cola would probably be the thing that would explain the bone density. So now we got to do a scatter diagram. So if you notice, with scatter diagrams, we can bring up our, actually, I should have probably had that ahead of time, so my bad. So if we go to our calculator sheet, chapter 4, drawing a scatter plot is all right here, right? So L1 will always need to be your explanatory variable. L2 will need to be your response variable. So, in this case, right, we know that L1 is going to be your cola. L2 will be your bone mineral density. So, after you plug those two in, what you want to do is you want to go to second y equals, hit enter on that plot number 1, make sure that it is on. Also make sure that none of the other ones are on. So only make sure that that number 1 is the only one that is on. Everything else is deleted. Everything else is off. So next you want to make sure that the type is the picture of the scatter plot, which should look something like that. Then hit enter. L1 should be list, X list should be L1, Y list should be L2. The only other thing you need to check that's not on here is you need to just hit regular y equals. Make sure that there's nothing in any of those equations. So just hit go to it and delete them. So that's the only other thing. So after you're done with this, just hit the y equals, make sure everything is okay. After you have done all of this, you're done. You never have to do this ever again. So basically all that we have to do now to draw scatter plots, and you'll see this, is to hit number 1, do step number 1, and then hit zoom stat, or zoom, which is right in the middle of your calculator, the top middle, and then just hit number 9, which is zoom stat. So you can either hit number 9 or you can go down and select number 9. But basically this is going to zoom in on our statistics. So after you go through the steps, all of these steps one time, all you have to do now is just, once you type in your data, just hit zoom stat and we're good. So when we type in all of this stuff, you may need to pause the video. I've already done this ahead of time, so it's kind of like when they bake the cake and they show you hours later what it should look like. So you should see this, more or less this diagram. If you don't, if it looks very off, that means maybe one or two of your points is off. Maybe you forgot to follow this list, so just read through it. Make sure you're doing every single step. Make sure that everything in the y equals, so not second y equals, but just regular y equals, hit y equals, and, which is the top left. And just make sure nothing's in there. Delete everything. Make sure that you have some, for every value in the y, you also have something in x. So make sure you actually typed in everything correctly. Go back and double check. Make sure that the cola was L1. The mineral density was L2. But yeah, we should get this. All right, we're going to skip part C and D for now and just move on to number 3. We'll come back to it though. So one classic application of correlation involves the association between the number of cricket chirps in a minute and the temperature. So in this case, which variable is considered an explanatory variable and which one is the response variable? So we're not saying that one causes the other. Again, we'd have to prove that. We're just saying that if there would be the case, which one would it be? Would temperature cause the chirps, or would the number of chirps cause the temperature? Well, hopefully you see, right, that the temperature may explain the number of cricket chirps in a minute, right? So the explanatory variable is your temperature. The cricket chirps is your response variable, which means this time, right, L1 needs to go for your temperature. You need to make sure to put the temperature in L1 and the cricket chirps in L2. So when we do that, when we graph our, put everything in the temperature in L1, the chirps in L2, and we hit zoom 9. So again, if you need to pause this video to do that, that's fine. But we should end up with this graph. Again, if not, just double check. Make sure that you typed in all of your stuff right. A lot of times, some people will accidentally put like 933 instead of 93.3, and that'll change drastically everything, right? So just make sure you typed in everything correctly. All right, again, skipping part C and D, let's move on to problem number 4. So listed below are the number of enrolled students in thousands and the number of burglaries. So in this case, which one would be the explanatory variable? Which would be the response variable? So would the enrollment possibly explain the number of burglaries, or would the burglaries explain the enrollment? So probably the more number of students that occurs, the more burglaries there will be, right? So the enrollment might explain the burglaries. In which case, L1 is going to be your enrollment. L2 is going to be your burglaries. So when you plug this into your calculator, right? So do the scatter plot. Go to stat, edit. Plug L1 into your enrollment, L2 into your burglaries. And then all you need to do is just hit zoom. And then number 9, zoom stat. And again, if you need to pause this video, that's fine. But what we should see is this, right? Now, if we look at these, so let's go back to problem number 2. So problem number 2, we had this diagram. What kind of correlation does this seem like it might be? Maybe a negative, right? We can kind of see things are going down. Maybe a negative. Maybe it's kind of all over the place. So possibly negative. If we look at this one, what kind of correlation could this be? Again, maybe positive, right? It's kind of, things are going upwards, so it could be positive. Looking at this one, right? So this was number 4. What kind could this be? Again, maybe positive. This one also right here kind of makes it seem like maybe it's nothing. It's just kind of all over the place, potentially. So then the question is, how do we know for sure? Because it's not always going to be exact and perfect. So how can we know? We need a cutoff. What's our cutoff? Well, now we got to talk about the linear correlation coefficient. So this R is what we call the linear correlation coefficient. And basically we know that that R is going to be between +1 and -1. So we can write it like this. So the least it can be is -1, the most it can be is +1. And what R is actually saying is that it is the strength of the linear relationship. It is the strength of the linear relationship. So the closer it is to -1 or +1, the closer it is to a line. So if it is 1, that is a perfect positive correlation. A positive linear correlation. If it is -1, it is a perfect negative linear correlation. So the closer it is to +1, the closer it is to being a positive linear correlation. The closer it is to -1, the closer it is to a negative linear correlation, which now, let's think about it. What would it mean if it had no correlation? So no correlation would mean that R would just be 0. Yeah, the closer it is to 0, the closer it is to not having a correlation at all. All right, number 3. If all the values of either variable are converted to a different scale. So let's say instead of measuring everybody's height in feet, you changed it to centimeters. Or instead of weighing everybody in pounds, you weighed them in kilograms. Well, if this is the case, the relationship between the two doesn't change, which means that R doesn't change. Likewise, the value of R is not affected by your choice of X and Y, right? The relationship between the two aren't the case. And because we don't know for sure that one affects the other, right? It really ultimately, for this case, for the purposes of R and determining if there's a linear relationship, it super kind of doesn't matter. Now, it will matter in the next section, so continue to do what we're doing. But if we're just talking about, are they related? Is there a linear relationship? It kind of doesn't matter. So interchanging them also does not change your R value. It does not change the strength of that relationship. And then lastly, R is going to be very sensitive to outliers. So one value can drastically affect it, right? And we can see this just kind of like this. If we have all of our dots like this, we can see that R is clearly going to be 1, or at least as close to 1 as possible. But then if you have one value that's here, right? Well, it's definitely not going to be 1 anymore. And that's going to drastically affect it. All right. So, rho is the population linear correlation. So, just like how we said mu is the population mean, and x bar is the sample mean, right? Everything about x bar also applies to mu, right? The way you find your sample mean, you add them all up, divide by the total. The way you find your mu, you add it up, divide by the total, right? Well, R is the sample linear correlation coefficient. Rho, and it kind of looks like a P, but it's a Greek letter rho, so make sure your P's and rhos are different. So I kind of think of rho as it's kind of like sigma, but you flipped it, and then it got lazy. It fell over. So that's kind of how I think about it. This is the population linear correlation coefficient, which again means that everything we just talked about with R also applies to rho. Which means the closer that rho is to 0, the more likely or less likely it is to being linear. So we said R, right? The closer it is to 0, the less likely it is, right? Because when it's equal to 0, there's no correlation. So since rho and R are the same thing, as when rho gets closer to 0, it gets less likely to be linear. All right, so we always want to test the claim that there is a linear correlation. So the claim is always there is a linear correlation. So you don't necessarily need to know this, just for the record, but this kind of explains where this is coming from. I'm trying to show you that essentially the stuff that we are doing now isn't all that different than what we've been doing all chapter 10. So if there is a linear correlation, so it could be, we could say that rho could be 1, right? But we don't care about positive. It could be -1, but again, we don't care about a negative correlation. We just want a linear correlation in general. So ultimately, what we definitely know is that rho isn't 0. Because if it was 0, it would be no correlation, right? All right, so step 1 is our claim. Step 2, counterclaim. That would be that rho equals 0. And then from these two statements, step 3, what's our null hypothesis? It equals 0 because it is always equal to 0. And what's our alternative hypothesis? From these two, it does not equal 0. So we can see that what we are assuming, right, if it's equal to 0, then there is no linear correlation. So we are assuming always, because we are always claiming this, so we are always assuming that there is no linear correlation, and we are trying to prove that there is a linear correlation. And this is true every single time, always. For any correlation coefficient, for any correlation problem, this is always the claim, counterclaim, alternative hypothesis, and null hypothesis. Every time. All right, let's do a quick review of those strategies that we've been talking about, right? So step 1, good, write your claim. Hopefully you've said that. Knowing these 8 steps are going to be a lifesaver. Step 2, counterclaim. Step 3, H0 and HA. Step 4, what tests do we do? And so we have 3 tests now. So the first test was one prop z-test. When do we use one prop z-test? When we are testing a proportion. We have t-test. This is going to be testing a mean. And now what we're going to use is lin-reg t-test. So lin-reg t-test is found in the exact same place that all the other ones are. So you can go to stat, over to test. And actually, if you go up, it should be about letter A-ish, I think, or F. It's like really close to the end. Yeah, so if you just go up, you'll get there quicker. So step 4 is going to be our test and test stat, or now linear correlation coefficient. So we'll talk more about how to use lin-reg t-test in a minute, as soon as we finish all these up. Step 5 is our p-value. Step 6 is our significance level. Step 7 is to reject the null hypothesis or fail to reject our assumption. And step 8 is our conclusion. All right, so let's go back to our example. So we said maybe for example number 4, maybe it's positive. Maybe there's no correlation. It's kind of hard to tell. So let's determine it. So we already have, right, L1 is your enrollment. L2 is your burglaries. We already said that. So what we're going to do is we're going to go to lin-reg t-test. Remember, that's in stat over to test. So to find your linear correlation coefficient, your X list should be L1 always. Your Y list should be L2. The frequency, each of these are occurring one time, so just put 1. So none of this should change. The only thing that's going to change is this part. And it changes accidentally. We don't change it, but we need to make sure that it doesn't change. And this is super important. So you can see that it says it's either can be less than 0, greater than 0, or not equal to 0, right? Which one are we going to choose? So hopefully you remember that we always said HA is that rho does not equal 0. So it always has to be does not equal 0. Always. But here's the problem. The second that you do t-test and you change it to greater than mu naught, it changes this to greater than 0. So on the homework, you're just going to get used to doing linreg t-test, enter, 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 done. Linreg t-test, enter, 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 done. Because you're always going to assume that it has your back and that it's going to be does not equal to 0. That is not the case on a test or practice test, right? On the test or the practice test, you need to make sure. Linreg t-test, everything's the same, but is this not equal to 0? Yes? Okay, let's move on. So that may be good just to pause every time you do it, even though it's a little asinine, right? But for the homework, it may be good just to pause and say, is it does not equal to 0? Yes. Okay, moving on. Okay, so after we do this, when you go all the way down, you'll see that R, not R squared, just R, is 0.561. So it asks to find the linear correlation coefficient, and this is what it is, 0.561. Now it says, does the linear correlation exist? Well, we got to keep going. So these are the first 4 steps, right? We already talked about the first 3 steps. Now we got 4. So let's talk about step 5 for the hypothesis testing. P-value. So if you go back all the way up, you'll see that the p-value is 0.0914. Step 6, significance level. So what's the significance level of this problem? So if you go back to the top, it didn't say anything about the significance level, right? So then what do we assume it to be? 0.05. Step 7. We see that the p-value is greater than our significance level. So then it's likely to be true, right? If our p-value is greater than, then that means that our assumption is likely to be true. So we can't reject our assumption. We can't reject our null hypothesis. We failed to reject it. Which means that there is sufficient evidence, or sorry, we failed to reject. So there is not sufficient evidence to conclude that, and let's go back. What can we conclude? So what did we say always was our claim, counterclaim, and all that stuff? So if we're keeping this, then looking at our our alternative hypothesis, what could we not conclude? We could not conclude that there is a correlation. So again, maybe there is, but we just need more data than this. So for what we have so far, we still assume, no, there is no correlation. All right, and we're just going to continue this. So let's go back. So we are on problem 4. Let's go back to problem 3. Remember, we put L1 the temperature was in L1, the chirps was in L2. So if you need to pause the video, make sure to plug all that back in. Then step C, find the linear correlation coefficient. So again, we can kind of skip the first 3 steps because those are always the same when it comes to hypothesis testing. So step 4, we do linreg t-test, right? Everything should be the same. The only thing we got to check is rho not equal to 0? Make sure that's the case. And then after we're done, when we hit enter, we see that R is going to be 0.874. So the linear correlation coefficient, 0.874. So, does a linear relationship exist between the two? Well, step 5, p-value. So when you look at the p-value, you see that it's 0.0046. Step 6, alpha. What do we say about alpha? It didn't tell us, so 0.05. The p-value is less, which means that our assumption is unlikely to occur, right? Given what we just found, the probability that is basically that our assumption is unlikely. So since our assumption is unlikely, we reject the assumption. So then 8. Because it's rejecting, we say there is sufficient evidence. There was sufficient evidence to assume something or to conclude something. There is sufficient evidence to conclude that, and then again, what are we concluding? Every single time, remember it's always the same. So if we reject our assumption, what do we keep? There is a linear correlation. So there actually was enough evidence to conclude that there is a linear correlation. And is it going to be a positive correlation or a negative correlation? Well, we can look both at our graph and at R specifically, right? Since R is positive, we know it's going to be a positive linear correlation. If you didn't get that, again, make sure to remember the temperature was L1, cricket chirps was L2. All right, let's go back even further. Let's do problem number 2 again. So remember, we said colas was L1. We said that the bone density was L2. This was our graph. So determine the linear correlation coefficient between the two. So again, we're going to have to use the lin-reg t-test. All you got to do is just make sure that rho does not equal 0. Yes, good. Moving on. So when you type all that into your calculator again, you'll see that R is negative 0.997. Really? That doesn't make... I'm going to need to double check this. Because that is not... Right? Because 0.997, that is really close to a line. This, though it looks pretty linear, is definitely not really close to a line. So I think I'm going to need to double check that in real time with you guys. All right, so we said L1 was colas. And we said that L2 was the bone density. All right. Okay, yeah. So we see that our R value is negative 0.760. I will also go back and just double check myself on problems 2 and 3, and if those answers were wrong, I'll post the actual results on the website. So hopefully you've already seen that by this point. All right, so that's our R value. So again, relatively close to 1, but a little far away. So again, to prove it, we need to do our p-values. So is there a correlation? It's kind of close to 1, but we need a cutoff. So we got to look at our p-value. So step 5, p-value. We see that our p-value is 0.0174. Our significance level is 0.05. P-value is less, which means that we reject the null hypothesis. So there is sufficient evidence to conclude what? What are we always trying to conclude? We're trying to prove that there is a correlation. All right. Okay, so let's do 2 more examples from beginning to end, and then we'll be done with this section. So listed below are the SAT scores and PSAT scores from prospective college applicants. The scores were reported by subjects who responded to a request posted by this website. So which variable would be the explanatory? Which one would be the response? So again, the idea would be that if one would affect the other, we're not proving that, but if it was the case, right, the PSAT would probably tell us about the SAT, right? Which means L1 is your PSAT, L2 is your SAT. So when you plug all those into your calculator, your scatter diagram, if you want to pause it before I show you, go for it. But this is what it should look like. So again, maybe positive, maybe it's all over the place. Let's see. So what is the linear correlation coefficient of this? So remember, we're going to do linreg t-test. Make sure that rho does not equal to 0. And we should see that R is 0.543. Part D, there is a linear relationship between the two. Is there or is there not? Well, looking at this, 0.5 is pretty far away from 1. So probably not, but let's be sure. We got to prove it using math. So looking at the p-value, we see the p-value is 0.1640. Part 6, significance level, there wasn't one, so we assume it to be 5%. And yeah, that's pretty likely to occur, right? So it's likely that our assumption was correct. So we failed to reject our assumption. We do not reject the null hypothesis. Remember, our assumption is that there is no correlation. You have to prove there's a correlation. So there is not sufficient evidence to conclude that there is a correlation, a linear correlation. Good. All right, last one. Number 6. Listed below. Oh, so what this is saying is that given what they said, right, that there is no correlation between the SAT and the ACT. However, what might be wrong about this? What might be a thing that we could see, oh, maybe this isn't as sound as we're thinking it might be? Well, how did they get their sample? It was from a voluntary response, right? Which means that this is a convenience sample, right? And we said convenience was a flawed method. So none of these results probably matter. But again, people do this all the time, right? They always are doing internet questionnaires and people get statistics from this, but that's a flawed system from the beginning. So another problem, we could have just stopped from the very beginning. But it's good to do the examples. All right, last example. Listed below are altitudes in thousands of feet and outside air temperature recorded by the author. So which one is probably the explanatory? Which one is the response? So probably the higher you go, right, the temperature would be affected by it, right? The higher you go, your temperature is going to change. So L1 is your altitude, L2 is your temperature. So when you plug all those in, and you put zoom 5, right? Remember, sorry, zoom 9. So zoom 9 is your scatter plot. Don't forget that. You should see this. Which, my goodness, this could not be more linear. I mean, it could probably, but like, what would we predict looking at this? What would we predict the R value is going to be? Probably super close to -1, right? I mean, this is almost exactly a line. So this is going to be really close to -1, we would suspect. All right, well, let's actually figure it out. So we're doing linreg t-test. Make sure your rho does not equal to 0. It is, so moving on. And when we see this, we're seeing now that we're getting the -0.997. Yeah, this is where the -0.997 comes into play, which is super close to -1, right? All right. So is it linear? Probably, but you got to prove it. Remember, the way we prove it is using the p-value method. So p-value. If you didn't say 0, you're wrong. Remember, p-value, p means probability. Can probability be greater than 1? No. So that means that you have an E negative, right? Which means you got to move it over. Another thing, right? It wouldn't make any sense for it to be bigger than 1 because that would mean that we'd have to reject it, right? There wouldn't be a correlation. But clearly there probably is, right? It's almost 1 or -1. So again, using these kinds of things when you're going through them can help you. So significance level is 0.05. So clearly 0 is less than that. So we are going to reject our assumption, right? The assumption is unlikely, which means that there is sufficient evidence to conclude a linear correlation. There's a quicker way of writing that. All right. So that is it. If you were a little confused, that's okay. We will be doing this again in the next section as well. But as always, feel free to email me, contact me, ask me any questions you need to. Have a great day.